Hi there, how's it going? Hope you're doing all right. Terry Brown, Mechanical Engineering here to go through another engineering mechanics uh, solution. So let's go and have a look at the problem. All right, so here's the problem. We have a bolted structure connected to ground down here, and we've got some loads acting on it. So we've got 1, 2, 3 forces, and we're asked to replace the loading system by an equivalent resultant force and specify where the resultant's line of action intersects the member AB measured from A. So 3 forces, we want to replace those 3 forces by an equivalent single resultant force. Now, usually the easiest way to do that is to find the result components of the force at A, and also the moment that we need there for to be equivalent to our original loading. So we'll find the equivalent force components and couple moment here at A, and then from there we'll find the single force. To provide some context for this, the first or the intermediate step that I just explained, where we find the force normal and the force tangent or shear force here plus the moment, we would use those to enable us to design the connection between this structure and the ground. So we'll probably have to bolt this into the ground. We might have some welds around the bottom here to the plate. So in order to size those welds and bolts, usually what we need to do that is the normal force, the shear force, right, or the tangent to this section, and the moment that's applied there. All right, so let's do the problem as it's written. All right, so our solution will be first find, as I said, find the equivalent force and moment at A. So I've just redrawn the problem here. As I've said sometimes before, it's a good habit to get into redrawing the problem, get used to drawing things nice, neat and clearly, thinking about where forces actually are, where the different parts of the structure or machine that you're analysing are really located. Okay, so try not to be lazy or just slapdash with this. Actually take the time and make sure that your witness lines go to where they're meant to go to. Right? So, putting dimension lines on, they're supposed to mean something. Right? So make them mean what they're supposed to mean. All right, so we've got our problem redrawn here. So firstly, finding our components, resultant components. Just sum up all of the force components of each of the forces in the x direction, sum of the components of each of the forces in the y direction, and then find the moment of each of the forces. Okay, so here we've got force in the horizontal direction, here a force in the vertical direction. We're already given perpendicular distances, and for this one we've got a force. Pretty easy for this with this force here to find the vertical and horizontal components, and then we're already given these dimensions here, so rather than trying to find the perpendicular distance from the line of action of this force to point A, we'll just use Baranoff's theorem or the principle of moments and find the components and find the moment of those components. All right, so let's get started, and before we do that, just indicate that we're going to take anti-clockwise as positive. All right, so looking at the forces in the x direction, we have the force at an angle here, that's at an angle given by the 3-4-5 ratio triangle. So if we want the horizontal component, that's going to be 3/5 times 5, so that's going to be 3, and then we've got our 8 kilonewton force applied over here. So 3 minus 8, that's going to give us minus 5 kilonewtons for Rx. And the negative sign indicating that it's going to the left. And then we have our components of forces in the y direction. So 4/5 times 5 over here for our vertical component in the negative direction, negative y direction, and minus 6. So we do that and we get minus 10. And that's acting downwards, as we can obviously see from the diagram. So to find the resultant of those, we just use Pythagoras theorem, square root of the sum of the squares, and we get 11.18 kilonewtons. All right, so now for the moments. Not quite now for the moments, working out the angle first, showing the resultant here, and I'm going to find the angle here, theta. You could find the angle theta in here if you want, or the angle around from the x-axis. Doesn't really matter, as long as it's clear what theta is, so that someone can look at your solution. Right? When they see theta equals a tan whatever, they can see how you've defined theta to be. Okay, so because I've defined theta here in this problem, the opposite side here will be Rx, so opposite over adjacent, inverse tan of opposite over adjacent, so Rx over Ry. Whereas if I'd found the angle in here, the angle around from the x-axis, it would have been Ry over Rx. Okay. All right, so let's put those numbers in, and we get 26.57 degrees. Show that on point A. Okay, so our resultant force in the x direction and our resultant force in the y direction, right, from these originally applied forces acting down here. But for this system to be equivalent to what we had originally, then we need to also have the moment working that out. So working our way through each force. So 3/5 times 5, so this is our force over here. Our horizontal component, 3/5 times 5, and its perpendicular distance will be 3 plus 0.5 plus 0.5, which is 4. I might just quickly draw that one in for you just to make that clear. No, it's not there. Okay, so that's that component, and once we draw that in, its line of action, right, is along there, and perpendicular distance, right, so that's its perpendicular distance. And then we also have, is it clockwise or anti-clockwise? So hopefully we can relatively easily see that that's going to tend to rotate around clockwise about point A. Right, so that will be a negative moment. Have negative out the front here. All right, so next we have the vertical component of our force over here. Okay, so there is the vertical component of this force that's out on the end here, and its line of action down like that. So clearly its perpendicular distance is there, right, which we can see up here will be 0.5 plus 1.5 equals 2, right, which is what we've got down here. And is that going to be clockwise or anti-clockwise? So we can see that that's going to tend to rotate clockwise about point A. So therefore we have another negative moment. Okay, so we have a negative out the front of this term. All right, so let's see which one I deal with next. So next we've got the 6 kilonewton vertical force here. Perpendicular distance will be 0.5, and again that's going to be rotating clockwise, so that one's a negative. And then we have our 8 kilonewton force up here. Perpendicular distance will be 3, and that's going to tend to rotate around that way, which is anti-clockwise. So therefore that one's positive. And I think that's it. So yep, do we put all that into our calculator, and we calculate 1 kilonewton meter for our net moment. So we can put that on our diagram to show that. All right, so at this point, we've now found the equivalent resultant force and its components, normal and tangent or shear at point A, and the resultant moment. Okay. So these are the things that we would need for designing this connection down here. If you want to design the welds and the bolts, and the strength of the concrete and so on. So we would need these things here. The original question though asked us to find the equivalent single force. So we now need to say, okay, where do we place this resultant force? Somewhere above or below A, so that its effect on the body is the same as this force and this couple moment. And of course, equivalent to the original three forces. Okay, so we need to move it somewhere. So I think we can see fairly obviously that we need to move it above. We need to move it up in order to get an anti-clockwise rotation. Right, so if we move it up somewhere and we don't know where that is, we don't know how far up we need to locate it. So we just label that with an unknown label D. I've also just put on here the components, the X and Y components, and we can see that RY passes through point A rather. Okay, RY passes through point A, so it will have 0 moment about point A. So therefore, we just need to make use of Rx in working out where D, or the value of D. The moment of Rx about point A will be Rx times D, and we want that to be equal to this moment here that we calculated before. So we can put all those, or firstly rearrange the equation to make D the subject of the equation and put those values in. So the moment was, 1 kilonewton meter, Rx was 5, so we can put that in and work out our distance D. Right, again, I hope that was helpful and provided more guidance and insight into dealing with equivalent systems, and also provided you with some context and some reason for why we want to determine the resultant forces and couple moment at some location on a structure. The other thing, of course, that we might need to do, let me just go back to the problem here. We've also got a bolted connection here at where this curved bit is attached to the vertical section. So you might want, well, in order to design this connection here, we would need to find the equivalent force and couple acting here. And in this case, we wouldn't include the 8 kilonewton force. We only need to look at the 6 kilonewton and the 5 kilonewton force. All right, so now we're done. All right, bye for now. Catch you in the next video.